from NCU today for the TH seminar. Professor Chiang, Cheng-Wei did his undergrad at NTU and received his PhD at the end of 2000 from Carnegie Mellon University, CMU. And then he spent 2 years as a joint appointment postdoc between Enrico Fermi Institute at Chicago and also Argonne National Lab. Then he spent another year at Wisconsin, working on light physics, and then returned to Taiwan to NCU, starting as assistant professor. And by 2011, he became full professor. And at the beginning of 2013, he became a distinguished professor and also the director of counseling center. Let's see, let me recall. Actually, throughout this time, he always held joint appointments with academia Seneca. He received a Young Theorist Award from NCTS and also received 3 times Outstanding Research Award from NCU. Am I missing anything?
Wow, you remember?
I have my short
very detailed.
My short-term memory is okay. I'll get everything after 1 minute. Okay, so that's so he's a phenomenologist, and he's going to tell us about the phenomenology of extended Higgs sector in Georgi-Machacek model. Okay.
Thank you very much. So first, I would like to thank Professor Ho for the warm invitation, and for me to have a chance to talk about my work in the past few years. In the past few years, I've been concentrating on this Georgi-Machacek model. It's a beyond standard model, new physics model, and so what I will report to you are based upon several collaborations with these group of people. Some are my postdocs and some my students. So I guess, as you know, the standard model all started with a question about the mass of the mediator for the weak interaction. And so in the year of 1964, 3 independent groups, totally 6 people, they proposed something we now call BEH mechanism to explain why the weak gauge bosons have mass through this BEH mechanism, which I will briefly introduce later on. And then came the question, what about the masses of the other elementary particles? It turns out that according to the Weinberg principle, as long as it's...
This is the first time I hear see this name on the screen.
Oh, okay. Yeah, I think people don't call it that way, but I call it Weinberg's principle. So the basic idea is that as long as the term is gauge invariant, you should add into your Lagrangian to consider. And so there's nothing to forbid such a Yukawa couplings in the Lagrangian unless you impose some special symmetry. Otherwise, this is allowed, and you can use the same Higgs boson to explain the mass of the fermions. So that's a very economic way of explaining the mass. So in the standard model, all the mass of all the fundamental particles are proportional to the Higgs vacuum expectation value. So that's actually a unique feature of the standard model. And that's also something we want to verify in future experiments. So now comes the question, how do we identify, how do we detect such a particle? Of course, now we already saw it, but in general, how do we detect it, and how do we determine the detailed properties of this Higgs boson will be the emphasis of the high energy experiments in the next few years.
So the function on Weinberg principle is what, like the mass is given by the VEV.
Sorry, I cannot hear you.
The Weinberg principle is what? The VEV, the mass.
No. You should consider all the terms that are consistent with your gauge symmetry.
So it's a strange term.
You can add such terms into your Lagrangian without any problem. So then in that case, if you don't impose any symmetry, then you should include it.
You're saying that all the terms
that are
noticeable,
yeah,
emitted by the velocity.
yeah. Yeah, the most general.
Yeah,
Lagrange.
nobody calls that Weinberg principle.
Yeah,
It's a
no.
general principle.
Yeah,
It's a
Yeah.
anything allowed by symmetry.
yeah.
Yeah.
But I think that was this point was first pointed out in the effective theory paper by Weinberg.
The next question would be why energy scale, right? Different energy scale, they have different symmetry.
Right, but
Yeah,
at
yeah.
this,
Leading-
yeah, at this scale,
Yeah,
all the
yeah.
symmetries you have is the standard model gauge group, right? So, a journey has set off to search for such a particle for almost a half century, and about almost 2 years ago, we saw these two plots to indicate that we found this Higgs boson, and the mass is around 125 or 26 GeV.
Are you sure it was breezy? I'm sure it was breezy somewhere.
It was breezy in Taiwan, because I remember vividly. That was my birthday. So I remember
wow.
vividly.
Your birthday.
Yeah, I have the same birthday as the Higgs boson.
And the United States.
Higgs is fun.
So now the question is, does the ledger end here, or we still have some other story to tell? And so here's the minimal Higgs model. You have the motivation was to use this this kind of kinetic term for the Higgs boson to give masses to the weak gauge bosons. And as I said, economically you can also, well, or according to what I call the Weinberg's principle, you can allow this kind of Yukawa terms in your Lagrangian. Therefore, you give masses to the fermions as well. So for the students, here's the Higgs potential, which is unstable. This symmetric point is unstable, and the Higgs field develops a wave spontaneously and drops down to the bottom of this potential well. Okay, all sounds very good, but in fact, this nice Higgs potential or Higgs turns out to be a Pandora's box, because again, this is to explain the mass of the weak gauge boson, but we have a constant term. In general, we have a constant term in the Higgs potential, which, if you want to use that to explain the current cosmological constant, then there's a problem with the fine-tuning. Why it's such a small number? Naively, you expect this number to be around the electroweak scale. Why is such a small number? The second question is, as you saw, the potential near the symmetric point, it first bends down and then curve up. And to bend it down, you need this mass term to be negative. And why is it negative? That's the standard model doesn't give that answer. It's just a parameter. Then this lambda term, to guarantee that eventually your potential curves up to ensure the stability, and also to ensure that the electroweak wave you have is the global minimum. And why is this term positive so that you have a stable potential? That's also a question. And even this term, originally we said that's good because it can explain the mass of the fermions. But according to the current spectrum, you'll see that the Yukawa couplings has a wide range from top quark, the heaviest one, down to the electron mass. It spans several orders of magnitude. And so why is there such a dramatic hierarchy? That's also something that standard model cannot answer. And it's all related to the Higgs.
But is this discussion meaningful? I mean, in the sense that this is tunable Lagrangian. Are you going to consider like a radiative correction, like 5 to 6, and like high power terms as well?
And how does that help with?
No, it doesn't. But the thing is that why do you only consider those terms? That's the thing. If you consider all the higher potential, if you have a radiative correction, it could be higher terms in your.
But this is what we have in the standard model, right? The higher the terms are not allowed in the standard model. You start with this Lagrangian.
You can have a 5 to this.
Renormalizability.
No, yeah, by renormalizability, you have only these terms. Of course, you have higher order terms, but that doesn't answer the questions that I mentioned.
Right, but standard model is an effective theory.
Yeah, okay, if you take that point of view, yes.
Actually, we're not sure of that.
Yeah.
It may not be an effective.
How do you know?
Well, okay. All right, okay. So, if you want to say standard model is interpolate to the point scale, then yeah. Okay.
Okay, so as I said,
but that would be problem in its own right.
so as I said, in the future we have an experimental program trying to probe this linear relation between the elementary particle couplings to the Higgs field and their masses. So we hope to establish this because this is very unique in the standard model. If you see any deviation in this linear relation, then that's an indication of something beyond the standard model. You have, for example, another Higgs field. So here it says exploration of complete Higgs land. So we want to see, I should mention, so when the muon was discovered, Rabi asked this question, who ordered that, right? So here I want to ask, did you know who ordered only one Higgs doublet, or maybe there are other Higgs fields as well? So we want to explore not only this part of the Higgs sector, we also want to know whether there's something beyond what standard model tells us. So if we found some signal of this sector, then that tells us that the current Higgs boson is not the only one, and maybe that provides us a door to the beyond standard model sector. And these will definitely lead us to new phenomenology of the Higgs boson. For example, you can have CP-odd Higgs boson, you can have even doubly charged Higgs boson, which I will tell about it very soon. And maybe it can give an explanation why the neutrino mass is like that, or maybe it can connect to the dark matter candidates.
By the way, this is an orthogonal direction to your previous page, because the previous page was saying why is mu squared negative, why, j, etc.
Yeah.
By addressing these, you only make the problem much more complicated.
These may not directly answer those questions in the,
Why it is connected to the origin of the neutrino mass?
I will show you in some models you can connect to the neutrino mass. Okay, so now what I want to ask this question, suppose we have not only the standard model Higgs doublet that participate in the electroweak symmetry breaking, we have another scalar. It may be a doublet, it may be a triplet, and so on. So the question is, what would be the best way to discover, to detect, to experimentally establish their existence? So there are two approaches. One says that you just measure the current Higgs decay with high precision to see whether there's any deviation from the standard model prediction, as I said, to check, for example, the linear relation. That's one direction. The other direction is to study the Higgs interaction with the weak gauge bosons. Remember, originally the Higgs was introduced to explain the mass of the weak gauge bosons. So in some sense, this is more fundamental to probe the electroweak symmetry breaking, the mechanism. And in fact, I will show you that even in this direction, there are two possibilities. You can study the gauge boson scattering, the longitudinal mode scattering at high energies, or you can study the fusion processes at lower energies. And I will tell you that, in fact, we think this would be the most convenient way of doing that. So here's the plan of my talk. First, I will talk about the vector boson scattering, and then I will try to persuade you why this is not the best approach to explore the electroweak symmetry breaking, even though many people say that this is a good way. Then I will tell you the Higgs triplet model, which then leads to the Georgi-Machacek model. Then I will talk about the vector boson fusion process and explain why these processes are better than the scattering processes. Then, if time allows, I will make some comments about the electroweak phase transition in this model. Okay, so there's a famous paper by Lee, Quick, and Thacker in the mid-70s. They explained that one should study the longitudinal components of the weak gauge boson scatterings at high energies, because at high energies, these longitudinal components start to remember they came from the Goldstone modes of the Higgs field. And in that case, if we can study it and verify the scattering behavior is as the Higgs model predicts, then that verifies the Higgs mechanism as the right mechanism for electrical symmetry breaking. So that's the idea, and it sounds very good. Here, let me show you, just give you some idea why this works and what kind of subtleties you have in here. So consider the longitudinal scattering, and in this case, at very high energies, the polarization vector of the weak gauge boson goes like this. The leading term scales like energy, the colliding energy over the mass of the W boson, and the second term is the inverse. There's no constant term in between, so that's the leading order term. And you are considering this kind of vector-vector to vector-vector scattering. So without really doing the calculation, you can just count. There are 4 external legs, so you have 4 polarization vectors in this diagram. When you multiply them together, you get e to the 4th power. And that tells you that the scattering amplitude of this process scales like energy to the 4th power. If you keep increasing the energy, the amplitude keeps growing and growing, and eventually it blows up. That's no good. That violates the unitarity of quantum mechanics. So
this argument has a flaw, because on the left-hand side it's a polarization vector, which is normalized to 1. So the argument is a little bit.
What's that? This is a polarization vector?
No, it's okay, but just saying that the polarization vector, no matter what, is of order 1. So as an argument, it's okay, but you're breaking some equality.
No, but I think if you square it, you multiply it by itself, then you still get 1.
But then you need a second term, I think. Anyway,
here I just explained it in powers of E over M. Yeah, I think this is correct. There's no problem.
Okay.
Yeah. Okay, so then you can organize your terms in the scattering amplitude in powers of E over M. Remember, the leading order is E over M to the 4th power, then the 2nd power, and so on. So these two are bad because they scale with the colliding energy, and that will violate those terms will violate the unitarity of the scattering process. Fortunately, within the standard model, as long as you have the right gauge structure, then if you include all the gauge terms, this term will disappear. A4 will be 0. And to remove this term, you need a Higgs boson. So if the Higgs BEH mechanism is the right mechanism, then A2 is 0. You don't have such a term. Then you're left with this harmless term in your scattering amplitude. However, if the electroweak sector is not just like what the standard model says, then the story will change. Here, let me give you one example. It's the famous 2 Higgs double model. Suppose I use this as the symbol for the Higgs vector boson coupling in the standard model. Then in the 2 Higgs double model, this will be suppressed by this sine beta minus alpha term, this vector. And the other heavier Higgs boson, presumably heavier Higgs boson, will be this same coupling times the cosine. Okay? So in this case, if I consider, for example, this WW scattering, there are 7 diagrams. The top 5 diagrams are the gauge diagrams, and the lower 2 are the one involving the Higgs boson, mediated by the Higgs boson. So if you do the calculation, you'll find that the gauge diagrams and the Higgs diagrams, they just cancel with each other, so that you're left with only the harmless e to the 0th power term. So this exercise tells you that first we need to have the right gauge structure. That's fine because the standard model was based upon gauge invariance, so that's guaranteed. And the second thing is that we need a suitable Higgs boson so that we can have this nice cancellation between the gauge diagrams and Higgs diagrams. But if the true Higgs sector is the 2 Higgs double model, then here it's suppressed by this delta factor. Remember, delta is this proportionality factor between these two. So it's suppressed by this one, and now the cancellation is not complete, and you get E squared growth in your final result. So that gives rise to the bad high energy behavior in the scattering. So if we will, so this work was done with Kimman and TC in 2008. So we studied the cross section as a function of the invariant mass of the W bosons in the final states. The standard model is given by, for example, this is the process that I was talking about, W plus W minus to W plus W minus. The red curve is the standard model prediction. So you see it has a nice high energy behavior. It keeps going down as you increase the scattering energy. But if there is a deviation in the coupling, like delta equals 0.9, then eventually at some point you will see, it's very difficult to see, it goes up, and like 0.75 it goes up like this. So that's the E squared growth in the scattering process. And it also happens in other processes as well. At that time we just assumed the mass is 200 GeV, but that doesn't matter. Changing this mass just shift the peak a little bit. The point is that you will have this kind of bad high energy behavior. So experimentally, at that time we thought experimentally, if you try to measure this process, you will you can probe whether there is another Higgs somewhere else. But very soon I realized that this is not very useful, because here we just study W plus W minus to W plus W minus. We assume we can have this kind of initial state. That's one thing. Second, we assume that we can measure the invariant mass of this final state. That's the second thing. But that's not the case, because we don't have a machine that produces only longitudinal modes of the W. And we cannot guarantee that the W we get in the final state is longitudinally polarized. So both assumptions are not valid. So after this project, I sort of gave up about the idea of studying vector boson scattering.
Like I said, I think in this older work, in this slide, you do not mention at all the heavy Higgs mass.
Yeah,
So
we assume that the heavy Higgs mass is.
But that's inconsistent when you vary delta to become smaller and smaller, right? You have entirety violation somewhere.
Right. But here in this work, we just want to.
Right, illustration. I think when we heard those things, we probably had similar discussions. So it's not just this experimental side.
Yeah, true. There should be another heavier Higgs somewhere, and then that will unitarize the scattering entity again. So the curve, these curves will bend down at some point. Yeah,
to find a peak.
But Kimman and the TC, they somehow keep pursuing this direction. So this is they did it in last year, and I just want to show you that here the black curves are the standard model predictions, and for example, if I take these red curves, they also consider the 2x double model, and again they assume the heavier Higgs mass is very, very heavy. So they got this kind of spectrum, and they claim that, oh, okay, you can see some deviation between so if you measure something like this, you can claim the discovery of physics beyond the standard model. But I want to point out that you probably cannot read clearly. Here is 10 to the minus 4, 5, 6, 7. 10 to the minus 4, 5, 6, 7 in the units of picobarn. And so in this, they assume the 13 TeV machine. So you can see that actually this deviation is very, very small. You need a large integrated luminosity in order to see the difference. Another thing is that, well, I see it here. So as I said, after the project with Kimman, I realized that this initial state W bosons are actually attached to one of the partons in the initial proton or antiproton. So you don't have polarization vectors for these two. So two polarization vectors are gone. And also the excess you see, according to their simulation, most of the excesses are in the high energy regime. So you need high energy collisions, that's one thing. And usually, as we know, experimentally, usually you have larger error bars in the high energy end. So this is too optimistic. Experimentally, you probably get a lot of big error bars in the large energy regime.
So actually, this is a log scale, right? So maybe some difference maybe not that small in the low energy as well. This is log scale to bias or high. I don't know.
Oh, you mean here? But again, one important thing is this the magnitude here, 10 to the minus 4, 5, 6 is too small, right?
True.
So that's okay. And also, it's very, I don't know experimentally how do you determine that the final state W boson is longitudinally polarized, but that's what you need, right? So that's another thing. And small cross sections, and they assume infinite mass for the other heavy Higgs. So all these arguments tell us that it seems impractical to consider the vector boson scattering. Okay, now let me switch gear to tell you the Higgs triple model.
The second Higgs get masses from their own self-interaction or from the light Higgs?
The second Higgs mass?
Yes.
It's given by it's just like the Standard model Higgs, the mass, you can have a mass term. Of course, in the Standard model, the mass term is negative, but once you redefine your vacuum your theory at the vacuum, then you get the mass. It's all determined by the Higgs potential. Put it
so second Higgs also has some potential?
Yeah, sure.
So the quarks are coupled with the first
Both. But well, it depends on which
the
is.
mass is the sum of these two. Is you have to adjust the two Yukawa coupling together, and then there's another. So that is the y times the phi of the first expectation value of the first.
There are different types of 2x double models. Type 1, type 2, type 3, type 4, or types X, type Y. People call it differently.
So there's a lot of flexibility.
Right.
So there's more things to tune.
Right. Yeah.
Less
if you think that way.
power. Less predicting power.
Yes, but so they leave those things to the experimentalists to determine. So in the Higgs triple model, you just introduce one Higgs triplet. So it has this. You can organize the fields in such a way, and then after introducing them, your Higgs potential becomes more complicated. Again, this is the Standard model Higgs doublet, and the mass term, and the self-interaction term. Then for the triplet, you have these kinematic term, mass term, and this term is important because here we want to let the triplet to develop a vacuum expectation value induced by the valve of the doublet. So you need this term. You need a coupling between the doublet and the triplet. And then here, I don't write it out, you have the quartic terms for the triplet field as well. And here, the important thing is that in this model, you can write down such a gauge invariant interaction, such a Yukawa coupling terms for the neutrinos. And it's you can see that it's left-handed and left-handed neutrino field. So that gives you a Majorana mass term. That's the so-called type 2 seesaw mechanism to give masses to the neutrinos. And the important thing is that in this model, you have this doubly charged Higgs boson. That's something you don't normally see in other new physics models. So people have studied this model that was introduced in the mid-80s or early 80s. So people have studied this model a long time ago. So people found that the decay patterns of the new Higgs bosons depends mainly on the valve of the triplet field. So if the